So in this lesson, we're going to dive back into the particle world with exploring another form of grains, which is vellum grains. And we're going to use it to create this sort of kinetic sand with a nice tricky reveal of this graphical word that we have in here. So to speak, we are going to be spreading the word, if you will. So I hope that you find this lesson enjoyable. I sure thought it was fun to create this one. So let's get into it. So to kick things off, I'm starting with my lesson 9B grain start version 1 file. And in it, there is this knife that I modeled. We just jump inside here. You can kind of see how I did that. I started with a box and then just did some, really just classic box modeling on this thing. Inserted some edge loops, etc., yada yada, all the way down here, and I added some animation right here and here, and subdivided it, etc. And so this right here is going to be our collision geometry for pushing around our kinetic sand like setup. And then over here, I did some additional modeling, and down here, you can see it's much higher res, and I added some little teeth to the end of the knife as well, just to help with the refraction effect and make it look a little bit more realistic when we are spreading. So that's what these two things are for. So one's for rendering, the other one's for simulating, which is fine. And so we're just going to have that to start off with. You can feel free to try and build your own if you want, or you can just grab this one and start from there. Either way, it should be good. But this is already keyframed. I didn't want to waste any time messing around with doing any of that end of it. So with that being said, we need to create some kinetic sand. So the first thing we need to do is we need to create an emitter. Let's do that. We're going to throw it on a sphere for that. And we're going to dive inside. So inside our sphere here, this is a little bit too big. I'm going to just bring it down by 10% by changing the uniform scale to 0.1. And then I just want it to rest on the surface. So we'll do our usual trick. I'm going to just bring transform, throw it on a transform underneath here. And then use our translate. We're going to translate in the negative direction of the minimum value of the bounding box. So bbox 0 dy underscore min. I could have just dy min, sorry. I could have just typed in 0.1 or 0.5, whatever. But just, I don't know, habit. Got to put in those expressions, get used to using them, etc. So now that we've got our emitter here, I'm just going to name this our emitter. I'm going to go up to my vellum tab on my shelf up here. And so now up here, what I can do is I can click the vellum grains button, and it should create a grain source for us and a grain sim. So you can see if I go back up to my object level here, I've got my knife. I'm going to turn that off. I got my emitter here, and I've got this grains is actually importing from the vellum sim. So this is where we'll cache everything out. And then we've got our DOPNet where the vellum simulation is actually happening. So we've got our emitter that goes into our DOPNet and then into our grains export. I'm going to just jump back into the emitter to see what it's done for us. So here it looks like it's created this grain constraints node. Let's just highlight that and take a look at it. It looks like it's trying to create points from volume. Our sphere is a primitive. I'm not seeing any of that. So if I highlight our geo, nothing's showing up. That could be because our grain size is a little bit too large. Let's try something like 0.01. Now we can see that we've got grains packed inside that sphere for us. I also, it's packing them in sort of a regular kind of interval. I want to just jitter that up a bit, and there's a jitter option here where we can do that. So it's jitter. If I tick this box on, it's thinking about stuff, and then we get this nice sort of much more random distribution. So we'll just go with that for right now, which is good. So now that we've got that, let's just go over to I'm going to turn off this import as well, and we're just going to jump inside the DOP network to see what we've got. By default, this should just blow up, or it's actually just going to drop these points down and do nothing. So let's just throw in a ground plane real quick. So I'm going to type ground plane, and then I'm going to wire this into the merge. And then because it is a mutual effector, so it should work out fine. But I like to just make sure the ground plane's going in on the left, because generally, like, this can be set to left inputs affect right inputs, like so. So I'm just going to hit Shift R on the merge, and that will make it so the ground plane is to the left and the vellum grains are to the right. So now let's just hit play and see what we get. We get all of our particles falling down. They're piling up a little bit, but not very much. And they're also sliding off in all sorts of different directions. So the first thing I'm noticing is we could probably mess around with the physical properties of these a bit, but I also want to emit the grains for a few frames, like 2 seconds prior to, and then we'll just shut it off. So the way we get that to work is if we go over to our emitter right here, you can see that the emission type is set to only once. I want to set that to continuous, and then I can keyframe this activation off after 48. So I could set a keyframe at frame 48 to turn this off, or I could just put in a simple expression. I'm going to put in at frame is less than 48. And basically this is going to make sure that activation is 1 whenever this value is true. So for every frame that is less than 48, this activation value is going to evaluate to 1, and then once the frame is greater than 48, it's going to evaluate to 0. So it's just kind of a cool way of setting the frame that you want it to turn off instead of actually keyframing it. So cool. Now let's just play this back and see what we get. I'm just going to zoom out a little bit and click play. And you can see that it is emitting grains. It's making a pile of sand. Everything's going. I mean, it's not very interesting at this point, but then once we get to frame 48, it should all just shut off. And it looks like it's just continuing to emit after frame 48. So let's see what happened here. I think that this might be one of those instances in which using the at version of frame isn't going to work, and we're going to have to use the dollar symbol. Just to test to make sure that this is working, I'm going to type in $F, and I'm going to just set it to some low number, like $F being less than 3. It should only emit for the first 3 frames, so I don't have to wait all the way till the end of that, just to make sure that that's actually working properly. So let's click this. Yeah, it emits for 3 frames. I can't even tell. Yeah, I can't even tell if it's actually emitting for 3 frames. Let's set it to 10 and click play. It's emitting for 10 frames and then it stops. That's good. So yeah, just one of those things. Sometimes if the at version of the variable doesn't work, like at frame doesn't work, then $F is the other one. So I just throw that in there as a troubleshooting thing. So back to the regularly scheduled programming. Let's just change this back to frame 48. And now let's start messing with some of these properties. First off, this is emitting a whole bunch of points and they're sliding all over the place. I want to increase the friction so that they kind of pile up a little bit more. So I'm going to increase friction by first going to the ground plane, going to the physical tab, and I'm just going to bring the friction on the ground plane down to 0.1. And I'll click play. And it's not doing much to affect it yet, but we're going to keep messing around with some of the properties on the vellum itself. So if we go to our vellum solver and select that, we can go to our advanced tab and go all the way down to the, we're going to go to the common tab, go all the way down to the bottom, and we can see we've got this static threshold and dynamic scale. I'm just going to crank these up. I'm going to set my static threshold to like 10 and then my dynamic scale to something like 1. So the static threshold basically is going to be, it's just sort of the static threshold more or less is there's friction that is being applied to these particles, slowing it down when these surfaces are touching. And the static threshold is really like sort of how much force it needs to experience before it will actually start sliding along that surface. Then the dynamic scale is really how much like impact to how much force to apply in resisting that sliding motion relative to what this force is on the static threshold. So now if I click play, you can see that these particles are really started forming a pile because they aren't experiencing enough force to really slide along our geo here. So it's really kind of creating this nice like pile for us, and that's really what we want. But it's really kind of uniform right now, and we want to create something a little bit more interesting with our pile. It is kind of interesting how we get these interesting strands that kind of stick up. I think that's because it is experiencing friction with itself that is causing some interesting patterns, and we're actually going to be creating a more dramatic version of this in our sim. But we want to kind of create like thicker versions of this, and we can do that by messing with the attraction weight. So in the Vellum solver, or in the Vellum solver, there is an advanced tab, and in here you can do all sorts of other kind of cool stuff. So if we go down to this section under grain collisions, there is a repulsion weight. By default, this is on, and its weight is set to 1, and it's using a repulsion like a repulsion force, if you will, of 10,000. That's basically saying it's basically, you know, when these particles collide with one another, how strictly are we reinforcing the fact that they shouldn't intersect with one another, and we use this repulsion force to push the particles apart. I think for this sim, I'm just going to leave that as it is, but I want to mess around with the attraction weight. And the attraction weight is pretty much the opposite. And what it does is it's just going to kind of suck the particles together. So you can create sort of clumping effects like you would have sand or something like that. So the weight actually is sort of like how it's factored into the sim, like how much it's actually considered when it's trying to determine whether it should be attracting or repelling things. So these two weights, you can kind of try to balance them out yourself. Or what I do is I would just tick this enable constraint averaging, and it's going to try to just do the best job it can to create a non-divergent sim out of these two weights. So I'm just going to turn the attraction weight up to a value of like 0.5 for right now. And then I'm going to crank the attraction value to 200. So this is sort of the force, and then this is sort of how much it's being factored into the total of these forces right here. And then there's mass shock, which I think is just like how shock waves of force travel through. I'm going to leave that the way it is. I'm just going to leave the rest of this the way it is for right now. And I'm just going to click play and see what we get now. So now we can see that we're getting this nice clumpy, chunky version of this sim growing, which is great. I like how it kind of creates these like interesting kind of branches that kind of come up and stuff. And then after frame 48, it should all kind of stop and start to just kind of fall down on itself like so. Cool. So because Vellum has applied these little sprites, it kind of makes it easier to see than if it were just points, like what kind of topology we're starting to get out of. I mean, it's not topology, but what if it was sort of a surface, like what kind of little chunkiness we're getting to it, which is cool. So the next thing I want to do is gravity is a little bit intense right now. I just want to kind of decrease the force of gravity a little bit. So our gravity is by default negative 9.8 meters per second squared. I'm just going to do a value of negative 2. See what that gets us. Let's go back to frame 1 and click play. You can see we're starting to get really, really crazy growth going on with this. And I could imagine that you could really create some cool stuff, like some very cool growth patterns if you were to kind of do this in zero gravity. You get these amazing branching kind of arms. It almost looks like those snake fireworks that you would light that would kind of light on fire and grow, you know, from like a little tiny pill shape to be this gigantic long snake-like thing. So now with this, what I found for balancing this is when we bring our collider through here and it starts spreading this stuff across, with this many substeps in our solver, we've got, if you look over here on our common tab, we've got 5 substeps on our solver. I found that that actually was too much. Like, it was actually allowing this sand to clump together, and I found it to be easier, and it made my sim go faster if I actually reduce the substeps to 2. And you can see that it'll dramatically change the way that this looks. So if you really want those large branches, it's a little bit more of a balancing act. You'll have to go back to your solver, go into the advanced tab and start dialing around the attraction weights and stuff like that to really get it to spread out nicely and still have a high number of substeps and still have that large growth. So there's sort of like a balancing act that is done there. But for the purposes of my example, I felt that turning the substeps down actually causes a more inaccurate simulation, but sometimes that's cool. You just want it to go fast and it actually gets you the look that you want in the end. So I'm going to just turn this down to 2 and let's take a look at what we got. You can see it's simming much faster. We're still getting some of these little tendrils, but they're falling over nicely, and they got a little bit of bounce to them, and it's just sort of creating this nice little pile of sand for us to spread around, which is great. So now that that's coming to rest, that's looking cool. I think it's now time we could start introducing our collider in here. So we've already got our ground plane as a collider, and I just want to merge it with our other collider that we'll bring in. So I'm going to throw it on a static object, and I'm going to wire that in here, and then I'm just going to go and select in my knife, my spreader. I want to get that spreader null that's under my knife. So we're going to hit accept, and I'm going to say use deforming geometry because I want it to be, I want it to update the geometry with every frame, because that transformation is occurring underneath. The transformation of the knife is actually occurring inside here. And you can see there's keyframes on this geo that's under our object level. We got to turn on deforming geometry. If it was just happening out here, we wouldn't have to. It would work fine. So back into the AutoDOP network, a couple other settings I want to affect, which is bounce. I want to bring the bounce down to 0.1, and let's bring the friction down to something like 0.01. I really want it to just slide right off that knife. Also, with the ground plane, I want to also dial the bounce down, now that I'm thinking about it, on the ground plane as well. Not sure if it really is going to make much of a difference, but I like to avoid the bounciness if possible when I'm doing stuff with that's supposed to be kind of gloopy and clumpy, like kinetic sand. Cool. So let's just rewind this and we'll see what we get. I'm just going to play this down for a little bit, and you can see our knife is out here. Pardon the terrible knife model, but it worked. It works enough for the render, and it works enough for the collision geo, so why not, right? All right, so here comes our knife. That sand is settling down nicely, and we should have contact. You can see it starting to push it around over here. That knife moves across our pile of sand. We've got little pieces flying off. That's cool. I love how it kind of feels the need to kind of bulge out as the knife goes over it. If I just rewind that a little bit, you can see it starts to kind of have a little bit of an undulation that occurs right in here after that knife passes over it, as it sort of needing to reinforce its expansion, as if it was under too much stress with the knife and it had to kind of equalize itself after the fact. Plus you get these little stray bouncies coming off, which is fun. Let's go back out here and click play some more. Awesome. So you get this nice spreading of this sand, and you get these nice kind of cracks. It's kind I don't know if you can see it in the recording there, but if I back out, you can kind of see that it gets this nice kind of cracking over here, which is really kind of, you know, the type of thing that you encounter with things like kinetic sand. So let's just oh, and you can see I ran out of cache memory, so I'm going to actually have to cache this again once I write it out to disk. I could have increased the amount of cache that I was allowed to use by going to my DOP network and going into my cache settings and maybe increasing this from 5 to 10 gigs. That way I wouldn't run out of info here. If you've got enough memory in your computer to do it, that's always an option. I might just do that right now in case I need to resim something so I don't have to think about it later, but it's not going to make any difference really right now. So what I'm going to do is just go down to the grains vellum node, and I'm going to jump in there, and I've got my vellum IO. The vellum IO is basically the same as a file cache, except it will also bring in constraints and stuff, which we're really not using in this example at all. But it's bringing in our geometry, it's removing normals, etc., and then it's caching it out to disk. I'm just going to name this differently. So I don't like caching my cache files into a geo folder. I like caching them into a cache folder. So I'm going to throw a cache folder in there. Then I like to name the cache inside of my cache folder based off of the operator name. So $OS, which is going to basically be vellum IO. And then I'm going to create a folder based off the file name just to note what version we're on. So $hip name. And then I'll let the rest of it be as it were. I only want to go up to frame 192, so I'm going to go down here and change this to 192. I found that for my example, I didn't really need any more frames than that to accomplish what I was after. And then I can save this to disk. But there's something that I want to handle first. I'm going to change first off the name of this to be something that makes sense to me. So I'm going to call this the vellum cache. But before I actually run this cache, what I want to do is create an ID on my points. So when we're inside of here, we're going to be doing something where we actually are going to copy colors back onto our IDs. But we're going to be copying it based off of a final frame that we have simulated. And so in order for these points to actually be able to look up what that attributes it needs from those points, we're going to have to kind of designate each point an ID number. Normally, it wouldn't matter. We could just use the ptnum or the point number. If you look in our geometry spreadsheet, when we go back out here into our emitter, you can see that we've got a whole bunch of points, and we don't have any ID being generated by these grains. But we do have a point number right here. And we also know how many points are being generated. We know that this is actually generating, it looks like 4,435 points per frame that's being emitted into our scene. So we can actually use the number of points that we have here and the point number and the frame that we're on to create a unique ID number that will carry consistently throughout our simulation. So I'm going to go and I'm actually going to split this view top bottom. So we're going to say split pane top bottom. I'm going to just right click here and turn on our geometry spreadsheet so we can see what we're doing. And then I'm going to use an attribute create. So attribute create, I'm going to create the attribute ID. I want it to be an integer because it's just basically going to be a point number, except we're uniquifying the point number for each particle as it's created based off of what time it was created. So we can put a little expression in here and just do some really basic math to determine that. So the value that we want our ID to be based off of is the point number. So we're going to start with the point number. Oops. Click that. We're going to start with the point number. If you accidentally click that and it becomes a 0, just click the parameter again. It gets back your expression. We're going to start with the point number, and then we want to add to it. What we're going to add to it is we're going to actually look at the number of points that are incoming. So there's a little expression for that, and it's called n points. And then we want endpoints from the number of points from the 0th input, or this input that's coming in right here. So that's really what this evaluates to. This is going to just change to whatever this number is. It's 4,435 points, just counting it up. So we want to add to it the number of points that we have, but we also want to multiply it by the frame, because that will, so if I do asterisk at frame, that will actually be taking however many points there are up here and multiplying it by the frame. So on frame 1, there's going to be 4,435 points. See, and it's going to be adding that here. Another thing on this attribute create is I have it set to a float right now, and I want it to be set to an integer. So now you can see ID as an integer. I'm just going to hide all these other things. So I'm just going to, under view here, I'm going to say hide all attributes, and then say I'm going to tick ID just so I can see the ID. So now if I go from frame, so you can see I'm on frame 83. If I go down, all these IDs are changing every frame. If I go back to frame 1, we start at ID 4435, which basically means that because we're on frame 1, we're already adding 4435. I actually want to then just subtract 1 from frame, so that when we start from frame 0, all these IDs will start to match up with our point number. So this is just purely for kind of aesthetic reasons, but I'm just going to put a bracket around frame and then say -1 and then add an end parentheses like that. So on frame 0, we're going from ID 0 all the way up to ID 4434. It totally matches up with our point number. But then on frame 2, boom, this goes up, this jumps up. So we go back up here and we are on 4435 and so on and so forth. So throughout our simulation, it's going to carry this ID attribute for every single point so that we can access it later and do some randomization. If we wanted to apply p-scale randomization to changing point count on our output, well, it would reseed every single time based off of ptnum, since ptnum is changing constantly in our export. So now having these unique IDs, we have a unique seed that doesn't change just because a point entered the sim. So now let's just go and cache this all out so we can see what we get. One thing that I just caught, tricky little thing, on the ground plane, I accidentally set the friction to 0.1. I wanted the ground to have a high amount of friction because I didn't want things to move around so much, and I wanted the bounce to be low. So I might actually bring the bounce down just a little bit more. I'm going to put it down to maybe 0.01, but I want my friction to be high. I'm going to bring the friction back up to 1. On the ground plane. Static object, bounce 0.01, that's good. Friction, really low friction, that's good. And I'm going to cache it one more time. It was maybe like a 1.5 minute cache on my computer, not too bad. So no big deal. All right, I'm going to hit save to disk one more time, and I'll be back in a sec. All right, so that is finished caching. I'm going to just tick load from disk here and click play, and we can see we've got our particles coming, and we can't see the knife, but it comes and spreads that all out like so. Cool. So I think that at this point we can do the cool trick, which is getting a texture to appear to be formed as this knife is spreading the grains apart. So the way I want to do that is I want to map attributes onto the final frame of this simulation. And the way I can do that is just setting up a time shift. So if I go over here, and this is inside our grains vellum where we've got our cache here, I'm just going to throw down a time shift node. And I want this time shift node. This time shift will allow us to sort of, pick any frame we want. Right now it's defaulting to whatever frame we're on. But if I right click and delete the channels here, I can just manually scrub through this and pick any frame I would want to see. So you can see that I'm on frame 192, but I'm able to pick any old frame from here, and it will display that frame. So let's just link it over here. We've got our end frame right here. I'm just going to copy this parameter and just paste it here so that whatever we end up caching, this is just going to pick the last frame from that cache. So now I'm scrubbing the timeline and nothing is happening. So what we can do is we can set our attributes here on this and then just copy it back onto our attributes that are actually moving. So let's go and create an attribute from map. And by default, attribute from map is pulling in this default texture that we have here, which is just a default, I guess, a UV kind of map tool or whatever, just to kind of give us a reference as to what's happening. So now if I were to just copy this over here, let's just see what happens when we do it on the sim itself. We got our attributes. That's cool. If we're above, it looks like that those attributes are just totally mapped on, and they actually swim. The particles swim, the textures swim through the particles as the particles are moved, and the attribute map actually tries to resize based off of like the bounding box of the particles. So it kind of stretches out, and it doesn't really sort of magically fall into place. It's just sort of always there. And I really want this to be random and then begin to form as the knife is spreading over it. So when we bring the attribute map over here, we have the attributes where we want them to be in their final resting place. We just need to copy them back onto these points based off of those final points. And that way it'll know that it can, that way it will know that it knows each particle is able to look into the future now, basically, and see what color it's supposed to be on the final frame and hold that color all the way back in time to the beginning of the simulation. So long and short, we throw down an attribute copy. So attrib copy, like so, and we wire in our actual cache right here into the left input, and then we copy what we want to copy in from the right. And now if I scrub this back, you can see that everything comes in all sort of jumbled like this, and then we spread it across, and then it reveals and goes into its right position. So it starts off all jumbled, and as we scrub across, everything magically winds up in the right spot. Now it's curious to me how I did not have to use the ID attribute by default on this. I created it anyways, so I might as well. So if I go over here and say match by attribute, and I use the ID attribute, nothing happens. But to illustrate why the ID is going to come in handy later, I'm going to just throw down a attribute randomize. And I'm going to randomize the p-scale attribute. So I'm going to go up here under attribute name and say p-scale, like so. It's going to be 1 dimensions, and I want the minimum value to be 0.001 and the maximum value to be 0.01. So we get these points that are various sizes like so. So now we're copying these attributes back onto our sand geo here, like so. Now we just need to get our texture map in here. So let's go back up to our attribute from map, and instead of it grabbing this UV color.rat file, I'm going to just pick our texture that I've thrown into the text folder next to our hip file. So here we go. And I'll hit accept. And let's go to the last frame, and we can see that it's like upside down. I'm going to just go over here in the attribute from map, and we can go to the image settings, and I think it's invert V. I'm just going to hit invert V to bring this sort of into the right space. And then maybe I can do a little bit of translation. I'm just middle mouse dragging on these parameters over here to get this in the right spot. Maybe a little bit more. Maybe I'll increase the just the amount of, if I increase the scale of this, it actually makes the image a little bit smaller, like so. And you can see that it's got our word all sort of laid out with these graphics. That's all working. And if I scrub back, they all kind of stretch out and become meaningless, but then form as that spreading occurs across the surface, which is great. in order to get this ready for Cinema, I want to create a Redshift proxy of it. I've got to get a little bit of rendering going on over here in Houdini. So let's go over here. I'm going to right click. If you don't already have a geometry spreadsheet, I'm going to right click split pane top bottom. I'm going to turn on my geometry spreadsheet. I think I lost it somewhere in there. So I'm bringing that back. And then the other thing I want to bring back is my, down here at the bottom, the Redshift render view. Because I got to do just some basic rendering in here before I can get it, so I can get it out as a Redshift proxy. So let's do one thing. Let's just go up top here. So I'm going to create a camera. I'm just going to go to my last frame here. To start off with, and let's just I'm going to hold down the control key and click on camera to make a camera out of the current view that I was in. It jumps out to the object level, selects the camera, everything disappears because grains vellum is not displayed, so I'm going to turn that back on. And let's just bring the camera in slightly. I'm just going to grab this handle and dial it like that. Maybe bring this to the left and bring this one up, whatever. So now let's look at what we've got in our Redshift render view. If I click render, nothing's gonna show up. And then so the next thing I want to do is I got to tell Houdini that, or I got to tell Redshift rather, on this Redshift object tag on our grains, since this is the thing that's rendering the particles. Go up to the Redshift object tab, and then go to the particles tab, and then say render object as particles. Cool. The next thing I'm going to do is create a material for this, just because what I need to do is actually plug in the point color, because we've created let's jump in here. We've created a point color attribute based off of this image. We need to get that point color attribute into Redshift, because if we render it now, it's just going to be gray particles. Like so. Not even gray particles. It's going to be white particles. While I'm at it, I'm going to just add a light dome so that I can see a little bit more of the dimension here. So let's go up to I've got a Redshift tab right here. If you don't have the Redshift tab, you can go into your shelves. You hit this plus icon, go to shelves, and then go all the way down here to Redshift. Turn that guy on. And then I'm just going to turn on the RS light dome. And I'm just going to fire off the render one more time. Cool, so that's starting to look like sand. Good. Then I'm going to just go over real quick one more thing to my output context. So I'm going to click on this right here, go to out, grab my Redshift ROP, go to the Redshift tab, then to the global illumination tab, and turn both these on to brute force. You can see it gets just a little bit brighter. It fills in those cracks. So let's get those color attributes on here now. I'm going to stop the rendering. We're going to go back out to the, we're going to go to the matte context now. So click on out up here. We're going to go to matte, and I'm going to create a new RS material builder. RS material builder, we'll call this particles. Oh. And jump inside, create a new RS material. And I'm just going to wire the output color to the surface, and then we're just going to grab the color from a RS point attribute and wire the color into the diffuse channel. So diffuse color goes to out color like that, and we want the attribute to be CD that we get. So let's just render this one off real quick. Nothing happens. I need to assign the material to my shader, or to my geometry. So let's go back to the object level and grab our grains vellum node and go to the render tab. And then we've got this material slot here. I'm going to select using this little selection picker right here. So turn that on, go to the matte, and select our particles shader, hit accept, and let's render this again. And there we have our particles being shaded. If I go back a couple frames, nothing's going to update. So if I hop back over to my output context, grab the Redshift ROP, go over to the IPR and click live IPR live SOP level updates. So I'm just going to click that, and that'll allow me to kind of scrub. Here you can see I can kind of play this back and get a little bit of that, you know, that shader's working as we go through. So I could just kick out a Redshift proxy of this right now, but it's really kind of more like Floam than it is like little kinetic sand particles. So I think that we could take this a little bit further and actually up-res this using some point replication. So basically what we're going to do is take all these points and then add more points to their initial positions and give them random scales and such. So to get a good view of this, I'm going to just go up here and just kind of zoom in. I'm going to hit spacebar F to frame it up. And we'll get in nice and close on these particles. And then we can actually duplicate these particles onto, we can instance more points onto these points using a point replicate. And now if I wire this in, before I wire it in, I want to just bring the number of points down. I don't want 100 points per point. That's going to be a little bit intense. I'm going to just start with something like 10. And I'm just going to wire that in and highlight it. And you can see that it creates many, many more points for each one of our points, but it's kind of hard to tell what's going on with them. So what I'm going to do is actually delete a bunch of the points out temporarily, just so that I can get a better view of what's going on. So let's throw down a delete. Just going to wire this in right here. And I'm going to say, let's delete by expression. That expression, I want to create a random number based off of the ID as the seed. And I want to check if that number is greater than 0.01, I want to delete it. It's not doing anything because we're set to primitives. Just change that to points. And now we should get, if I turn off this template flag, we get much less points. So before, after. So now we can kind of focus in more on what's going on. In fact, I think I might take this down even by a power of 10 and say anything greater than 0.001, delete it. So now we just have a couple points that we can look at. I find that it's like handy to do this when I'm post-processing my points because it can help you identify any unexpected kind of glitches that might be happening in your particles, which we'll see in just a second. So now if I turn on point replicate, you can see that there's these little clusters that are created. If we zoom into one of these, you can see it's instance a bunch of little points onto our point. I'm going to just tell this to bring along the source attributes. So that's going to bring along the sprite for us and allow us to see the sprite in our chunks here. So another thing I'm going to want to do eventually is to randomize the p scale. So I'm going to throw down a attribute randomize. And I'm going to randomize the p scale. I don't want to just like, so what I can do here is let's just put p scale in. And when I randomize that, it gives me a huge value between 0 and 1. I actually want to just multiply the original scale that we already had by some other new range. And I can do that by going to, instead of operation set to set value, you could do a multiply. And so what that'll do is if we look at our geometry spreadsheet and go back to our point replicate, our original, I'm just going to select our view, hide all attributes, view, show p-scale. Our original p-scale was something on the order of 0.004. So now if we add a multiplicative randomization to it, it's just going to multiply these numbers by a value, a random value between 0 and 1. So if I go down here now, you can see that all these sizes have shrunk relatively because the maximum scale would be multiplying by 1 and the minimum would be multiplying by 0, and then there's just a range in there of different sizes. So really now what it's kind of all about is packing all of your points into an area that kind of resembles the rough area of one of these points, these larger points that we had before. So good values for that would be, I found that actually bringing the uniform scale of the shape generated by the point replicate, if you look here, if I bring this shape up, you can see that this uniform scale up rather, you can see that that controls how far apart it's replicating these points and spreading these points. You can choose different shapes that you can clone into, but for point number for only 10 points, it doesn't really matter. It's such a vague amount. But I mean, if we crank this up, you can see that it's trying to pack it into spheres or boxes. I'm just going to go with boxes because it's probably the fastest, and we don't have a very large number of points when we are only doing 10 points per point. I found that a good size for the shape was something around 1.5. For me, that just helps ensure that these particles are overlapping a little bit. And then if we bring back our point scale, so I'm going to just go back and forth between our original points and then our scaled and replicated points. And you can kind of see them taking up roughly the same area, but just having more detail in general. Also, what I did find was that this minimum and maximum value for the randomization multiplication was just a little bit much. I actually don't want my points to scale all the way to 0, so I'm going to just bump this up a little bit. Let's say 25. And while I'm here, I'm seeing that my p-scale is generating a 3-dimensional attribute, and I only want 1 dimensions for that because it's just a scalar. And then I also don't want my maximum value to go all the way up to the old point scale. You can see some of these points are actually achieving that old point scale. So I'm actually going to bring the max value down to something like 0.5. So now we get these little clusters of points that fit roughly. If I switch back and forth between delete and the attribute randomize, you can see that roughly those points are sticking in there. So point replicate is really sort of just a rough way of just adding more detail to your sim. Your results may vary with it. You know, sometimes using this type of technique can make it really obvious that it makes it really obvious that the sim has been up-resed and it's not doing what it's supposed to be doing. But for a fun project like this, I thought that it worked out pretty good. So the next thing that I want to explore is just what the motion of these actually looks like. Because when I was doing this project originally, I ran into a major issue that caused me to have to re-render. Because if you look really close, I'm just going to hit play. You can see that all these points are coming out, but if we kind of just focus on them, they're actually rotating and choosing all sorts of different directions and stuff like that. And so what's that all about? One of the things that Houdini does to determine what direction or orientation a point should be facing, if it doesn't have a normal, it computes it to point along its velocity vector. So let's go back to our original attribute or our original delete right here. If I throw up this normals, this normal really doesn't show anything. We do have velocity attributes here. So if I middle mouse click, you can see we have velocity. We don't really have a normal. It looks like our velocity trail might be so short that we don't really see any sort of tail. You can see some of these particles have tails on them. So let's just illustrate. Let's just try and see what it's doing to try and orient our particles by just doing a quick copy. So I'm going to copy a cube onto all these points. Just throw it on a box. Oops, I did wrong copy. I want the copy to points, like so. And put the box in the left and the points in the right. And let's just bring the box scale up a little bit. And take a look at these guys. I'm going to turn off the velocity trails. So without normals or any sort of orientation information, these particles, Houdini is on its own trying to orient these particles along the velocity vector, which isn't what we want, because as the particles come to rest towards the end of the sim, they are moving very subtly in many different directions, and it creates this kind of jittering effect. And you might not notice it at first because what we're working with is just so many points. It just looks like a jarbled mess, but it can lead to things like having to completely re-render your project because at the end of the day, you get this really noisy pattern. And it looks like kind of like TV static or just noise in general on your thing. So what I would do at this point is just actually add a normal. Because adding random normals will override this orientation that it's trying to just come up with on its own, and kind of keep it explicitly defined so it's not trying to do all this spinning about. So let's do another attribute randomize. And I'm going to put that right here, and we're going to choose N. instead of CD here. So we're going to randomize the normal. We want to randomize it inside of a sphere. And let's just take a look at those normals real quick. If we go back to our delete and just turn on normals, you can see we've got normals oriented in every which way. But as these points are coming out, those normals are not changing direction at all. So when we copy our points to it, and let's turn this off. Now, when we copy our points to it, you can see that if we go off to this section over here where they were jiggling around a lot, now they're all very stable. They're all pointing in their directions, etc. You know, and for a sim like this is going to work. It might not work for every type of sim. Obviously, maybe some sims you'll want to add your own little rotations to it or some subtle movement. But for this sim, I thought that just keeping these normals locked down, these rotations locked down, was the best way to go. So now, and this is also like an unexpected thing, you know, when we actually do this point replicate, the point replicate actually orients the distribution of these particles based off of those normals, or the velocity vector if it doesn't have normals, and that's what will lead to sort of this staticky, bad looking sim. But now if we play these down, you can see that all of our little points are just sort of holding their position nicely. So no funny business. Again, let's just go back to sort of towards the end here where the particles are coming to rest. Everything is moving very slowly and everything is looking very stable. If I go and just one more time turn off the normal randomization, you can see that these little points, little clusters are just rotating every which way, and it's just not a good thing. So that's a little fix in there, and we're gonna just let's just name some of these things since we're starting to get quite a bit. We're going to randomize the N, and then we're going to also down here we're going to randomize P scale, and let's see. So the next thing, let's just turn on all of our points by turning off. We're going to disable this delete node right here. So I'm going to flag that off, and let's just go back to sort of our camera position here. And we can see that we've got like a much denser mesh. It takes a little bit longer to calculate because it's got to, you know, compute all those. It's copying these points onto all these other points. But we get a much more high detail looking sim in the end. So one thing that I'm seeing right now that I would like is maybe to just add a little bit more randomization just to make it look slightly more realistic. We've got like our edges looking you know, very well defined, which is okay. But I thought maybe it would add some more realism to the whole scenario if individual points picked out of this jumble were colored random colors from this entire sand. So let's create a attribute VOP that will randomize the color of all of our pieces. So let's do that. We're going to throw down an attribute VOP, and we're going to wire it in here and dive inside. So what we did was we created IDs before. So if I throw down a random and I use our ID like this, and then I just create a ramp. A ramp parameter like so will be a color ramp, and I'm just going to wire the random value into the color ramp and wire that out to color like so. And it gives us this grayscale value, a bunch of random colors in this grayscale range. I actually want to use the range that was from our original image though. So let's just go here. I'm going to double click on this notch. And what I can do is click this button right here. It's sort of up on the top bar. It says show image to pick colors from. So we can click that. And then what I can do is, it's already loaded my image in here from before when I did this, but we can click this, that little page icon like so, and go into our texture folder and grab our image. I'm just going to make this a little bit bigger so I can see it. And right now we haven't created a group to specify which points we want to randomize, so we're just going to randomize all of them, and then we'll lock it down a little bit later. So I'm just going to click on this image, and it brings up our image here. And so for this notch, I can use my color picker. We'll just make it blue. And I think that between these two colors, I don't want a linear interpolation. I want it to be constant so that it is just stepped from one to the next. So we're going to want 25% of our particles to be blue, 25 to be yellow, pink, and green, or this minty color, spearmint color maybe. So this next color we'll do is let's pick yellow for that one. And we're going to set its value to 0.25. And then we can add 2 more notches and set this next one's value, its position rather, to 0.5. So that's halfway through. And we'll color pick this pink value right here. And then the last one we're going to set to a position of 0.75. And we'll color pick this spearmint color like that. All right. So now we've got our confetti cake over here of all these different random colors. So now let's create a group that will allow us to sort of only say we want to affect just, you know, maybe a small percentage of this entire particle system. So I'm going to call this attribute VOP randomize color. And then I'm going to create a group above this. So right before going into this attribute VOP, we can create a group expression. And group expression is just another way to form groups. We can create a new group. It's going to be a point group. And we'll call this the random group. And in here, we can choose a percent chance. There's a preset here under expression. It says 30% chance, and it will basically look at it'll create a random number out of the element number, which is similar to our ID. I'm going to just wire this into our ID just because that's an attribute I created earlier that I would like to use some more. And then what we can do is, you know, if we wanted to do 30%, we could leave this here at 0.3. Let's just do it for right now and see what happens. So here now, down on my randomized color, if I choose the random group, it only randomizes 30% of our little clusters. But I mean, this looks like it's actually a bit too much. So I'm going to just bring this back to maybe 0.01. So it's a smaller percentage that are random. Maybe that's too few, so let's maybe bring it up to, let's do 0.05. So a few more spots, but I really would like it to be, I don't want the randomization to actually occur on the entire cluster. You can see that all of these, it's actually randomizing the color of an entire chunk of replicated points. Why is that? That's because up here, you know, at this point in our entire setup, our points, if we look at our attributes, our ID has been replicated as well. So 0.0 does not correspond. 0.0 is not the only point now that corresponds to ID 0. Because it's been replicated and we copied those attributes up here on our point replicate, we said copy the source attributes. It copied the ID onto those points, but for every, you know, if it created 10 points per point, it's going to copy that same ID to all those new 10 points. So you can see that we get all of these, we get all these IDs, but we really need to have a unique ID for each point in order for it to truly randomly pick individual points after we've done this replication. So what we can do is recreate our ID using some attributes that are created by the point replicate. So the point replicate, if we actually throw down, they have got this keep source attributes option here. This is these attributes are, there are some attributes that are created in order for the point replicate to kind of do its thing. And if we turn those on, you can see that we get a source index and a source point. This source point sort of corresponds to our original ID, and then the source index actually gives us a number that is telling us which number or which point number or which copy number these we have created that we're on. So just using a little bit of using a little bit of some VOPs, we can actually rebuild a new ID attribute and then feed that into our randomized group expression here. So let's create that. I'm going to go up here. Let's go up after the point replicate, and we'll create a new, we'll update our index right here. So I'm just going to drag these three guys down here. Let's go in here and throw on a point VOP. So with our attribute spreadsheet open, we can use that as sort of our guide to get our math right here. But we're going to do something similar to how we created our ID attributes at the beginning of this lesson. We're just going to go in here. We're going to use the ID that we already have. We're going to want to bind in the source index. So let's go and bind in source IDX. It is a integer type. So we're bringing that in. And if I now, and then I'm going to need to bind export to ID. And I'm just going to call this ID, and its type is an integer. And if I just wire source index into ID, over here you can see that our ID has changed to our source index. Cool, so that's the first step. But what we need to do is we need to add some more data in here. So let's run, what we want to do is take our source index, and we want to add from our source index a multiple of what our original ID was multiplied by the number of points in our point replicate. So the number of points we're copying is going to be this 10 points per point. So if I go down here, I can create an attribute or a parameter. So I'm going to throw it on a parameter. And this parameter is going to be points per point. Points per point, and then I'm going to label it points per point. Label can be whatever you want. Really, either of these can be whatever you want. So now if I jump up here, I've got a little parameter that I can do a paste copy relative reference. So I'm going to go back to the point replicate, right click on the points per point, copy the parameter, go down to the point VOP, and paste relative references. So now if I click, you can see we've got a 10 there, which is good. And that 10 now is feeding into here. And so I can multiply this with our original IDs. So let's throw on a multiply. And wire in the ID number and wire in the points per point, like that. And now what I can do is just add this to what we're doing up here. If I wire that in, and we check over here, our IDs go from 0 on up. And then once they get to 9, where they were replicating again, now, it was going to go and start over. Now we're going up to 10, 11, 12, and so on. And we have, once again, a unique point per point. So now what we can do is we've got our randomized p-scale set. That randomized p-scale, we can actually, if we want to be explicit about it, we can make sure it's seeded to our ID attribute, even though it looks like it is already. And then we can create our group expression based off of that ID. And you now can see that our group is just selecting individual points and not clusters of points. So if we go, just to illustrate that, if I go back here and I deactivate this point VOP, that group is selecting these little orange clusters. And I turn this back on, and now it's selecting individual points randomly scattered throughout the entire mass of our sim. So now when we go to randomize the color, it actually pops in little pieces of confetti throughout the entire thing, and they're not just like little clusters, but really rather individual sand particles, which is cool. So let's just take a look at what our render looks like now. It looks like this is frame 71. So I'm just going to bank this into the preview thing here. And then I'm just going to go back to frame 71 in our timeline and just render this one more time to just see what the difference is between this old look and the much higher res look that we have now. So let's get into my camera here, and I'm going to click the render button. It's kind of hard to see right now, but it is much higher res. I just don't have very good sample settings going on here. Maybe if I switch over to my output context, grab my Redshift ROP, go to the Redshift tab, and under my settings here, I'll just crank this up to 128 as my max samples and 16 as my min samples. That should clear things up a little bit, make it a little bit easier to see. Just going to stop this. And maybe also turn on fixed scaling, set this to 100%, and maybe crank up the scale to 200% so that we can see a little bit better here, and then I'll click play again. And now if we get in real tight, you can see all of our little sand particles all mixing together. Got a bunch of random sizes, and when I back out, you can see that it all is looking much sandier, much denser than what we had before, which was this more uniform look. Now, after we've got all this sort of gnarliness going on. Awesome. I'm just going to stop that. So the next thing is to get this out of Houdini and into Cinema. So let's go back to our object level and just go into this grains vellum here, and I can create a let's create a Redshift proxy output. So we're going to type in, I'm just going to hit tab and start typing proxy, and that gives us this Redshift proxy output. And if I wire this in here, our range that we've worked with, we can set the range that we want to export. So let's set a frame range of 1 to 92. That works good. And then under our archive here, we can choose which file name we want to output to. So I'm just going to create a folder called rs proxy. So that's going to be the folder that it's going into. Then I'm going to name the file after the current hip name, and then name this also after the hip name. So we're going to have in our project folder a Redshift proxy folder, and then it's going to have a folder named after this current project name, and then again the file is going to be named after this project name. So now that we've gotten it to this point, we don't need to enter in a SOP path because we're actually feeding this directly in here. So don't worry about that. Now we can just render this to disk, and click render to disk. And over here, it's created our folder, and it is writing out these .rs files onto disk. Like so. And so you're just going to want to wait around for this to go through for a few minutes. I'm actually going to stop it just to move things along a little bit quicker. So I'm just going to interrupt this. I've got enough pieces here that I can actually just get this running in Cinema pretty quickly. So I'm going to open up Cinema. And in here, I want to... I always want to make sure that I don't leave my IPR running in the other program. I've done that quite a few times and had some computer issues as a result. So let's, under our Redshift menu, I'm going to create a new Redshift proxy object. And in here, under the path, I'll just choose, I'll hit Control G to, Control G gets my listery to go to this directory that I just had open in Explorer. And I'm going to open this file. And then I'm going to go to the animation tab, choose simple. I want to choose 24 frames a second because I tend to do my projects at 24 frames a second. And I did my sim at 24 frames a second in Houdini. So, you know, just to be something to be aware of when you're working between the two programs is to keep your frame rates in check. And then I'm just going to click detect frames, and it detects frames 1 through 22, which is cool. Also, because Houdini is at a scale of meters and Cinema is at a scale of centimeters, we just got to multiply this up by 100 in X, Y, and Z. So now you can see a little bounding box starting to form of our particles that are coming in here. So that's good. Then just want to get in here and kick off a render to make sure that everything came in. We shouldn't have to actually add a shader or anything at this point. It should all be here. So let's just add, I'm just going to add a dome light like we did before, so I can have some form of illumination. And then I'm going to hit, I think it's Control B. Yeah, Control B to bring up the render settings. And I'm just going to, looks like I accidentally created a new file also. Yeah, I must have hit Control B and Control N at the same time. So I'm going to go back to my untitled project over here and hit Control B again. And I just want to turn on GI in Redshift just because, I don't know, I just like the way it looks. Then I will open up my Redshift render view and click the play button, and hopefully, with a little luck, our particles are going to show up in the middle of our render view. And there they are. So from here, you can go on to continue to light and build out your scene, and you should be good to go. So that does it for this lesson, and in the next lesson, we're going to be looking at how we can animate strands like hair or wires using vellum and attaching them to a animated character in a way that looks kind of cool and interesting. So stay tuned for that.